All right, so I want to jump in and actually take a look at the multiple choice section of the second exam that I gave you. And we're just going to jump in and take a look at some of the problems. So we have a position versus time graph. We have positive acceleration, and we want to know what the position graph looks like. So let's just eliminate some choices here. So first of all, A, B, C, clearly there is no acceleration here. This is actually constant velocity. This is positive constant velocity. So the first is not moving, positive constant. The second one is negative and constant. Now we want positive acceleration, which is actually indicated by graph D, where we're moving forward and the slope is increasing. So now a ball is thrown straight up in the air from 1.2 meters above the ground. So let's see, so here's the ground. Here's 2 meters up. It goes all the way up to 5 meters and then falls back to the ground and winds up at 0. So its displacement from the starting point is 2 meters below where it started, because it's actually final position minus initial, and that would be 0 minus a position of 2, which is negative 2 meters or 2 meters below. Next, we have this 500 kilogram sports car that accelerates from rest, reaching a speed of 30 meters per second in 6 seconds. We want to know how far it's traveled. Notice this mass here is actually a distractor. And since we start from rest, I'm going to use an abbreviated version of the equation, which is this. So I'm going to leave off the end part. So I have x equals 1/2. Now the acceleration, that's going to be the velocity divided by the time, times 6 squared. And so I'm going to end up actually getting 1/2 times 5 times 36, which is 5 times 18, which ends up being 90 meters worth of distance. All right, now if F1 is the magnitude of the force exerted on a satellite and F2 is the magnitude of the force exerted on the Earth, this is clearly one of those third law problems. And notice they love throwing the word magnitude in there, and I told you you can pretty much ignore that word. You might just say if F1 is the force, and if F2 is the force for all practical purposes. So this is a third law problem where these forces are in fact exactly equal. Now, for number 5, and by the way, that answer is choice C. Now for number 5, we've got this situation. Let's draw a free body diagram. I'm going to call this, I'll just label it a 0.9. Whoops. I just love writing 9.8, don't I? So this is the 0.9 kilograms. We've got a tension going up, and we've got its weight going down. And then for the 0.6, we have the same tension going up, but we're actually going to have a different weight going down. So I'll call this W of 0.9 and W of 0.6. Now, the direction of motion is going to be this way, where the 0.9 kilograms is dragging the 0.6 up, and we need our sign convention to obey that. So let's set up our two equations. We're going to have W of 0.9 has a tug of war with tension, and the effect is that that 0.9 kilograms accelerates. And in the other direction, we're going to have the tension pulling on the 0.6, pulling against the weight, and that's going to make the 0.6 accelerate. Now, when we plug in the numbers here, this is going to work out to be 0.9 times 10, which is 9 newtons. This will be 0.6 times 10, which is 6 newtons. So we're going to end up getting 9 minus t equals 0.9 times a. And t minus 6 equals 0.6a. We can actually add these two equations together, and when we actually do that, we're going to end up getting an acceleration of 2 meters per second squared. I'm going to let you work out the algebra on that. That's kind of one of the things we need to do for AP Physics is I kind of need to get you to a point that you're actually doing this algebra and finishing up. So I'm going to leave that as an exercise to you. In the next video, I'm going to try to get through problems 6 through 10.